Uh, Hello, my name is Frederico, and I will be speaking about how to use Ruby to make 3D graphics in real time using Vulkan. Here I have an example of a functioning game running in Ruby. It's this software you see here running, it's built on Ruby, and in the back end, it's using Vulkan to rendering graphics. As you can see, there is a texture in the top. There are 2 polygons, some text rendering, and also some 3D cubes here with dynamic lighting. Also some input. It's getting some input from my keyboard and interacting with it. Okay, so how does it work? So as Yukihiro Matsumoto said, Ruby is simple in appearance, but it's very complex inside, just like our human body. And when I was developing this engine, I tried to use the same pattern that Ruby uses, that is to have a interface that is easy, simple, but inside is very complex, so it rides from you all the complexities of how the engine works inside. Here is an example of a code using the Candy Gear game engine. It's so simple that if you are used to Ruby, you probably can figure out what it's doing just by looking to this code. The first line, it creates a texture from an image. Textures are how the 3D graphics gives lights to the object it's rendering. Meshes, in the second line, it's creating a mesh that is the format of the 3D objects. Then it's created association between the mesh and the texture. If you ever played a game where you have several guns or characters that have different colors, but they are the same objects, then you know how this association works. And then the next line, we have an instance. Instance is how we render the same object in several different positions. Like grass, if you have a lot of grass in several places, you use instancing. Views is a region of the screen that we use to render something. So if you are playing a game with, for example, 4 players, you have 4 views, 1 for each player. And then there is the camera position of each view, so from which place in the world the game is going to be rendered. And last, there is the tick model that the only thing it does is to render one object here. I'll explain more about the tick in another slide. So why I'm doing Candy Gear and why it's good for developers. So we have a lot of game engines in the industry right now, like the Unreal, the Unit, the Godot, and they are, for me, they are bloated because they add too many features to make the development easier for newcomers. But when you are a more experienced developer, those functions, they actually can become problematic. They can also slow you down instead of make you go faster. And there are people that prefer thinner interfaces. This is why, for example, we have in Ruby, we have Ruby on Rails that is a little bit bigger, but we have some thinner alternatives like Sinatra. Ruby, it's a multi-purpose language, while some of those game engines, they use a specific language like Blueprint, Visual Scripting, or Godot. So if you learn those languages, the only place you can apply them is in those engines. But if you learn Ruby, you can do a lot of different things. So I think it's preferable to learn and work with a language that have several applications than spending your time learning something that you can use just one place. Also, the Blueprint Visual Scripting from Unreal, that is a very famous engine. It's a binary blob. The scripting, it's visual, but it's binary, and if you ever worked with Git, you know how hard it is to manage binary files. So by using a language like Ruby, you have this benefit when controlling your version of it. Also, Candy Gear is good for our community because Ruby, for now, it's mainly for web development. Every time I see someone working with Ruby, it's 9 out of 10 times he's doing something web-related. And I believe we should expand our language to other places and here games. Also, when we are testing the language, we are mainly testing with web because this is what we mostly do. So by having Ruby running outside in other fields, we can see how good it is for in other situations. Also, if we have some good engines with Ruby, we can attract game developers to our community and make our language more popular. So when I started making this engine, I tried to create with Yarv because it's the most famous implementation of Ruby. But I had a problem, big problem, that is the Ruby code, it's calling my C++ game. And I had to fine-tune everything for the garbage collector of Ruby, and I had a lot of problems doing it. And what I did to fix is to move the engine to mRuby. mRuby, it's more interesting because first the engine starts, and then it provides an API to the Ruby code, and only call the Ruby code when I needed it. So I just need to share some resources with the game and with Ruby, and while the engine can do all the heavy lifting without the Ruby bothering about what is going on. So the engine, it used the Hollywood principle that states that instead of the game calling the API of the game engine, the game is actually calling the engine is calling the game. Here is an example of this API working. So first there is a config method that the game must provide to the engine. And it's called before the engine is fully initialized. So it's where the game can give some configurations to the engine and tell the engine how many frames per second it wants, the resolution of the game, the name of the game, and things like that. Then the engine calls the config. After calling it, it finishes the initialization, and then there is the init method. In the init method, we can create some things we cannot do in the config, like textures, models, and so on, because the engine was not fully initialized in the first call. And then there is the tick method in the end that is called every single frame. So the game goes, the main logic game comes here. And there are 3 callback methods here, the key down, key up, and quit. They are called when the game receives some input for the player, like if he is quitting the game or pressing a key or releasing a key. Those methods are going to be called. So, multi-threading. Starting threads and finish them is very expensive. So one technique we use when doing video games is to start all the threads in the beginning and then finish all of them in the end. So we have all the threads in the beginning of the game, and then we keep just sending jobs to them. It's important to have just no more threads than processors, otherwise we are going to make the game slower instead of faster. Internally, the engine needs to initialize the Vulkan. The Vulkan first, you need one instance or more. Each instance have one or more physical device. These physical devices are the graphic cards that you have in your computer. So if your computer have multiple graphic cards, the interface provides you several physical devices. Then you need to choose what device you are going to use by creating a logical device, and each logical device has one or more quills. Those quills are how the graphic cards do multiprocessing. So before we can send a job to the graphic cards, we must create some command buffers. Command buffers are like instructions for the graphic cards. What the engine does to improve the performance is it caches every single draw command that the game does. So every time you tell the game to render something, it's going to create a cache. After it caches everything, in the end of the tick method, it creates several command buffers and delivers them to the graphic card, so we can do parallel processing into several different queues. Graphic pipelines. So when we are rendering 3D graphics, we need to use graphic pipelines. Graphic pipelines is a way to optimize, to render faster than we render something if you use CPU. For each kind of different image that we want to render in the game, we use a different graphic pipeline. So here are some examples. We have graphic pipelines to render 3D models, 2D models, the sky in the background, another one for large bodies of water like sea, a pool, a river. Here is how the 3D graphics pipeline works. If you are rendering a textured model, I don't know if, okay, you can see a texture model in the top. We use five numbers for each vertex. A vertex is a point in a 3D space, but also it have UV that is for texture. So as I said, you use texture to give colors. So we have an image that maps to a 3D objects, and this UV is how you map it. If you don't need any texture, you can just draw some wireframes, and you don't need the UV coordinates, just the spatial coordinates. Each polygon is a triangle in the 3D space that you need 3 vertices, and a mesh is a group composed of a group of polygons. And sometimes to save memory, we can use several vertices for creating the same, to create several different polygons. And we do it by indexing the vertices and using them through the indexes. We can also use 3D graphic cards to render 2D objects. 2D objects are just through sprites. Sprites is just a rectangle from an image. So in the top you have 3 images, different images. And down you have the 3 sprites are used to render those shapes separately. And because we are using 3D graphics, we take advantage of all the functionalities and make those images become polygons and render them as polygons in the same way that you do with 3D graphics. Also, there is the cube maps. Cube maps are a way to render the background in the game. Usually use them to render the sky. And because we can look the sky in any direction, we need it to be, we needed to see it for any direction we look. So what the graphic cards do is it uses 6 images. It samples all of those images as if they are one. So if you look to a corner, it doesn't look like something strange, like you are looking to 3 different images. It's actually rendered as one. It have a smooth effect. So here is the structure of a graphic pipeline. As I said, there is the input, indirect buffer, the indexed buffer, and the vertex buffer that I explained. There are the descriptors that are optional data that you attached to the graphic pipeline. And here in the center, we have all the stages of the graphic pipelines. Some of those are optional. Some of those you need to configure with a code. Those within the box with colors are customizable. And in the left, you have where the graphic pipelines renders the output. The color attachment is the image that is going to be displayed in the screen. So before we can attach data to the graphic pipelines, we need to load it. Usually it is compressed to save memory, so the game engine needs to decompress it, then it needs to convert to the format that is required by the graphic cards, and then it needs to move the data to the graphic cards, because usually the graphic cards has a different memory from the CPU, so we need to move this. But in some platforms like the PlayStation 5, they share the same memory, so you can skip this step and have better performance. And in the end, after loading of this, it returns a Ruby object, so the game can use the data to render something. So every graphic pipeline has a different layout. The layout explains to the graphic pipeline which kind of data it's going to be attached to it. And it's divided in several different descriptor sets, so you can attach each data as needed. In the example I give in the beginning, we have the world, that is something that every single 3D views have. That is, for example, ambient light that comes from all directions. Directional light is a light that comes from just one direction. This is why you had that effect that when the cube was rotating, one face was always brighter, is because of this data. Also, we have the view. We had two views in the example, the view in the top with 2D images and the view on the bottom with 3D images. So the view in the example, it needs a camera position, a camera rotation, and a projection. Projection is when you want, for example, an isometric 3D view is when everything has the same size, though it don't have depth like in real life. Or you can have a very open projection like in those fish eye cameras. And model instances, as I said, you can have several different objects in the same place. So for each object you are going to render, you need one instance, send a different instance to the common buffers. So here is an example of the graphic pipelines of each stage, how they work. So the first stage is the draw stage. It receives the command of what needs to be done, and then the next stage is the input assembly. It's going to receive all those data that I said, like the vertex is the index buffer and the vertex buffer. This square, it represents the screen, and the triangle represents the object that's going to be rendered. So in the first stage, it receives the object. In the second stage of the graphic pipeline, it's convert the object to the position it has depending on the perspective of the camera. So you can be seeing something from behind, from the front, from the top. So in the vertex shader, in the second step, we change this position. As you can see here, the object is slightly outside of the screen. So then there is the tessellation stage that actually are 3 stages. I'm simplifying here in just one. It subdivides the polygons into smaller ones and can apply transformations to them. This is a way of, in some games, when you are seeing something from closer, you want some smoother view of the object. But when you are rendering something from distance, you, for performance optimization, usually want to render a simple object, because if you spend too much rendering power, rendering something that is small, you end up having a bad performance. The geometry shader, it's similar to the tessellation, and but it's more powerful, but also more expensive, and it has several use cases. They are a little bit complex to explain here, but they can be used to render the same object in several places. For example, like when you want to render grass or something like that. After that, after you make all the transformations you want or not, so both the geometry shader and the tessellation, they are optional. You don't need to do then with 3D graphics. But after you do all of that, you have the vertex post-processing that is going to finish to assemble the object after all the transformations. And as you can see here, it removes a portion of the object that was outside the screen. Up until this point, we don't know exactly where the objects are going to be, so we keep computing objects that are outside the screen, but now we know where they're going to be, and the vertex post-processing is going to remove those parts that we don't need. Rasterizer. So after up until now, objects are just 3D coordinates in the space, are just geometry. In this stage, it's going to transform those 3D coordinates in actual images, in actual pixels. This is what we call rasterization. After the rasterization, there is the fragment shader that is going to apply color to those objects created by the rasterizer. And also it adds some depth to the object. The depth is how the game knows what is on top, what is on bottom. So when they go to the color blending, that is the final stage, it knows which object it must render, so it prevents an object that is far away to be rendered on top of something that is closer. Because we don't have a distance anymore when we have pixels. The pixels are all flat in the screen. There is still a lot of things to be done in the game engine. I'm far from finishing it. I still need to finish the multi-threading system. The multi-threading system, I need to finish it in the CPU level so it can deliver jobs in parallel to the back end, that is the Vulkan engine. And after that, I need to finish the graphic card. So the graphic processing that you saw now, it's not using multiple cores yet, not in the front or in the back. Also, I need to create a default file format for the engine. That is how the engine is going to load those images. For now, it's unstable format. Also, I have to create the audio engine from scratch. For now, I'm using libsdl to do all the audio in the engine. I also want to create some MIDI synthesizer to make it easy to make some audio for the game. For now, the game is only running on Linux with Vulkan, but I want to start making it run on Windows also with Vulkan. I want to port also to Nintendo and PlayStation, and I don't know where else I will port after. The SDL was a library that I used to make my life easier, but I need to remove it to improve the performance of the engine. And if you want to know more, if you're interested in working with understanding my engine, it was just an overview, you can look at all those references. So there is the Vulkan tutorial that is a tutorial for absolute beginners. If you never had done anything with 3D graphics, you can look at this first reference here, the Vulkan tutorial. If you have some knowledge of 3D graphics, you can go straight to the second reference, that is the Vulkan programming guide. There is a book, excellent book, but it's not for beginners. Also, there is this Kohi game engine. That is a series of videos that explain everything that I explained it here, but very slowly. So if you are entirely new, both to game development or 3D graphics, you can go there. It's going to explain everything you need to know. And also, there is my engine here in this link. If you want to see my code or you want to contribute, I will be very thankful because there is still a lot of things to be done. And that's it. Does someone have any question? Okay, so I think that's it. And thank you.